Good morning, dear all. I am Badra Guendouzi. I was a master's student at the Higher School of Computer Science in Algeria, and actually I'm a PhD student at Lignac Research Laboratory in France. I sincerely appreciate this opportunity to present for CISIS 2022 our work about genetic algorithm-based aggregation for federated learning in industrial cyber-physical systems. In the beginning, I will introduce the problem related to decision support for ICPS. Then I will present the related state of the art that helps to show our solutions need. Consequently, our framework FIGIA ICPS will be detailed and we will show its effectiveness through the experiments. Finally, I will conclude my presentation with a conclusion and our ongoing work. I start with an introduction. So industrial cyber-physical systems are CPSs that support Industry 4.0 and 5.0. They are used in industrial environments like manufacturing and production, which deploy industrial sensors that collect a high amount of heterogeneous data to make decisions in real time. That's why federated learning has been integrated with ICPSs to take decisions locally without the need of a central server, which helps to preserve local data. As a consequence, ICPS performance and productivity will be improved. Obviously, during our state-of-the-art study, we found that with federated learning, ICPSs are decentralized and support heterogeneous components like robots, cameras that generate a high amount of heterogeneous, private, and decentralized data. Thus, we need not unique training models that are different in terms of learning and architecture, but can deal with computational resource constraints, since in general, an ICPS cannot train gigantic models. On the other hand, unfortunately, the most existing works use a fixed server to run the federated learning, which doesn't ensure always its availability because of attacks, breakdown, or limited computing resources. So due to these limitations, our goal is to design and deploy a framework that connects several industrial plants for collaborative learning in order to improve decision-making. It might cover more machine learning techniques like deep transfer and federated learning that explore different ICPS components as cloud, fog, and edge computing, and finally enhance the federation by relying on genetic algorithms. So by surveying recent contributions that proposed cloud, fog, or edge-based federated learning, we have observed that MNIST is the most used dataset with a focus on heterogeneous data. Then convolutional neural network, which is a deep learning model, is applied in general when MNIST is experimented. Afterward, centralized federated learning architecture is used for all levels except peer-to-peer for edges. Further, the aggregator is not dynamic and applies federated averaging aggregation method in general. And finally, security is rarely ensured by encryption or blockchains. So to enhance the federation process in ICPS, we have proposed FedGIA ICPS that runs in 5 steps. The first is ICPS deployment, where we need some entities that can be edge, fog, or cloud nodes, a network to ensure their connections and define tasks to be executed by them to achieve the system goal. In the learning step, we prepare data to be clean data sets, which are used to train local models that are evaluated using loss and accuracy values. Transfer learning is also applied in this step. Next, each node candidates to take the role of the aggregator server. So we need the physical and logical attributes of each of them, like memory, capacity, CPU, etc. A specific algorithm to execute the election process and the score to classify the entities. After the election of the best entity as an aggregator, we move on to the next step, which is the aggregation method, where we need all local models, a specific algorithm, and the aggregator server in order to have a final global model. To move on to the final step, where the aggregator broadcasted to the different entities in the network. The architecture of our framework is composed of 4 system layers. First, the IoT layer in green color, which represented by a set of IoT devices, actuators, and sensors that collect data and apply actions according to commands. Then the edge layer, which groups a set of industrial zones that are represented by with the blue color. And each zone contains industrial factories, which are represented by the color yellow. Each plant has its own dataset and learning model where deep learning is applied. Next, the fog layer, where we find fog nodes in blue color, and each node presides over an industrial zone. They are responsible for storing local models and transferring them between different entities. And finally, the main cloud layer, which contains a single server, which is responsible for federated aggregation by default, aggregator selection, and local models transfer. So first, we define an ICPS by a tuple of set of entities, E, a network N, a set of tasks T, and a specific context CT. We start with an entity, which is defined by an ID, some attributes, an actuator that shows the status of an entity, a function M that associates to an entity its own machine learning model, a set of atomic actions, and its behavior in the system. Next, a network N is represented by a set of entities, channels, protocols, and a function read that connects the entities. A task T is a function that depends on a set of pre-order goals. And finally, a context CT that is defined by a tuple of a subset of entities, a subset of tasks, and a set of rules and policies. In the learning step, we choose the CNN as a base model for our experiments with the MNIST benchmark dataset, which is a dataset of 60,000 small square 28 times 28 pixel grayscale images of handwritten single digits between 0 and 9. It is distributed to edge nodes in heterogeneous manner, or more precisely, to not independently and identically distributed sub-datasets, which means that all edge nodes have an equal size and distribution of data. Transfer learning applied in our framework is fine-tuning the feature extractors, where only convolutional layers are transferred between entities when they have not enough datasets or computational resources to train their models. For the aggregation, we have proposed FedGIA algorithm that uses a genetic algorithm to choose the best weight vector and minimize the loss function of global model tested using a fraction of datasets of each edge node. Here, the local models are divided into base layers, which are communicated to aggregator, server for aggregation, and personalized layers, which are stayed locally just for training. So the inputs of our algorithm are C is the fraction of clients selected to participate in each communication round. The K clients are indexed by small k. B is the local mini batch size. PK is the dataset available to client K. G is the dataset used for the test, which is available on the aggregator. WB is the vector of base layers. WP is the vector of personalized layers. And finally, E is the number of local epochs, and the eta is the number of learning rates. And the output is the global vector of base layers. So at the beginning, the server initializes the initial global base layers vector that is broadcasted to all the clients, which are edge nodes in our case, for the update of their local models. And they generate updated base layers, which are shared again to the server for aggregation using genetic algorithm that is represented in line 9. This process is repeated until the convergence of all local models. The client update procedure aims to update the base layers, trains both layers, and returns the final local base layers to the server for another federated learning round. FedGIA schema is represented here. We have first the initial population that represents the vector of base layers of the selected edge nodes. They will go through the evaluation using the loss function of the global model tested with the dataset available on the aggregator. Then it selects the best vectors and makes crossover and mutation productions to produce a new generation. And finally, a global model is generated with the global base layers. So we tested our proposal FedGIA using 4 edge nodes, 50 federated learning communication rounds, and the 2 types of data for each experiment. So on the left, the results using the independently and identically distributed data show that is a remarkable improvement of an average accuracy for edge nodes 1, 2, and 4, greater than 95%. And on the right, using independently and identically distributed data, we see rapid convergence of all of them compared to other algorithms. So to conclude our presentation in this initiative, we have developed a new federated learning paradigm, FedGIA ICPS, using a new aggregation method based on genetic algorithms to choose the best vectors of weight. And we attempt to incorporate more federated learning techniques like selecting automatically and dynamically the best agents Also, we target decentralizing and securing the models using a proper blockchain. And finally, our focus is evaluating the framework on the more use cases and benchmarks. So thank you for your attention.